I hope you were able to see my introduction to solvents and solutions. We can now discuss a key topic of chemistry, which is acids and bases. There are three definitions of acids and bases. There is the Arrhenius acid-base theory, the Bronsted-Lowry acid-base theory, and the Lewis theory of acids and bases. Each theory gets broader and encompasses the earlier theory. Number 1, Arrhenius acids increase the H+ concentration in water. Arrhenius bases increase the OH- concentration in water. Number 2, Bronsted-Lowry acid-base theory says that in a solution of any two reactants in any solvent, including water, acids donate protons H+ or positive charges to the base reactant. Bases receive protons or H+ ions or positive charges. Number 3, a Lewis acid accepts an electron pair from a Lewis base. Conversely, a Lewis base donates an electron pair to a Lewis acid. Arrhenius acid-base theory restricts itself to aqueous solutions in water. Bronsted-Lowry acid-base theory is essentially Arrhenius theory extended to any solution. Lewis acid-base theory is even more general and encompasses both Arrhenius and Bronsted-Lowry theory. Both Bronsted-Lowry theory and Lewis theory require that acids and bases exist together in the same solvent. The solvent itself could be one of the reactants. For most purposes, the Arrhenius definition of acids and bases will suffice to explain how acids and bases work. In older texts, the word alkaline was often substituted for base, as the chemicals most commonly used to create basic solutions were hydroxides of alkane metals such as lithium hydroxide, sodium hydroxide, or potassium hydroxide. So, a basic solution and an alkali solution are nearly synonymous. Basic solutions that do not contain alkali metals are rare. In Arrhenius theory, water can be its own acid and its own base. In any container of water, there is a constant interaction between water molecules. H2O is a polar molecule, with the oxygen atom being more negative and the hydrogen atoms being more positively charged. Sometimes one water molecule will steal a hydrogen ion H+ from its neighbor if the negative oxygen comes in contact with the positive hydrogen. The result will be the creation of a hydronium ion H3O+ and a hydroxide ion OH-. The equation for such an interaction is shown. The subscript L indicates liquid. The subscript AQ indicates the ions are in an aqueous or liquid water solution. Here, the first H2O reactant is the acid or proton donor, and the second reactant is the base or proton receiver. The resulting product is a hydroxide ion OH- and a hydronium ion H3O+. In a Bronsted-Lowry context, these products might be called the conjugate base OH- and the conjugate acid H3O+. Some texts might simply write the equivalent equation shown, where a water molecule spontaneously divides into a H+ ion and an OH- ion. As a free proton, H+ could not remain detached from a water molecule very long in an aqueous environment. The original equation with the hydronium ion H3O+ is more realistic. Just as in gas-gas reactions, reactions in solution have a temperature-dependent equilibrium constant. Acids have an equilibrium constant usually labeled Ka. Bases have an equilibrium constant usually labeled Kb. Water has an equilibrium constant usually labeled Kw. If we go back to the original water-water reaction equation, we could write an equilibrium constant for water. Just as with gas-gas reactions, the water equilibrium constant is the concentration of products over the reactants. With gas-gas equilibrium, we use only gases and leave out the liquids and the solids. Likewise, in aqueous reactions, we only use the AQ concentrations and leave out the liquid and the solid participants from the equilibrium equation. So Kw is hydronium ion concentration times hydroxide ion concentration. Now at a room temperature of 25 degrees Celsius, Kw is 1 times 10 to the negative 14. So at 25 degrees C, we write Kw as hydronium times hydroxide equals 1 times 10 to the negative 14. If the water at 25 degrees Celsius is neutral, neither acidic nor basic, then the concentration of hydroxide ions and hydronium ions will be equal. And both ions will have concentrations equal to 1 times 10 to the negative 7th moles per liter. So, the acid and base equilibrium constants Ka and Kb in neutral water are both 1 times 10 to the negative 7th at 25 degrees Celsius. It's interesting to note that the number of hydronium or hydroxide ions in 1 mole of water is only a small fraction of the total number of water molecules in that 1 mole of water. A water molecule has a mass of 18 AMU, or water has a mass of 18 grams per mole. Water has a density of 1,000 grams per liter. A liter of water has a mass of 1,000 grams. In moles, a liter of water is 1,000 grams per liter times a mole per 18 grams equals 55.5 moles per liter. If Avogadro's number is 6.022 times 10 to the 23, the liter of water contains 3.34 times 10 to the 25 water molecules. If the concentration of hydronium ions, H3O+, is 1 times 10 to the negative 7th moles per liter, then a liter of water contains 6.022 times 10 to the 16th hydronium ions. So, in neutral water, the ratio of water molecules to hydronium ions is roughly 500 billion to 1. So, a very small fraction of neutral water is hydronium ions. Chemists find it tiresome dealing with exponential numbers. So they often use a logarithmic scale to convert the exponentials into numbers that are easier to grasp. Chemists use the pH and pOH scales as replacements for the exponential equilibrium constants Ka and Kb. pH equals negative log 10 Ka. pOH equals negative log 10 Kb. So, neutral water has a pH of 7 at 25 degrees Celsius. pOH equals 7, and pKw equals 14. And we can see right away that pH plus pOH equals pKw equals 7 plus 7 equals 14. Remember, with exponentials and logarithms, multiplications and divisions can be handled with simple additions and subtractions. In fact, if one knows the pH, one can get the pOH by subtracting pH from 14. On the pH scale, the lower the pH, the more acidic the solution. So, any aqueous solution with a pH below 7 is considered acidic. The higher the pH, the more basic or alkaline the solution. Any aqueous solution with a pH greater than 7 is said to be a base or alkaline solution. To get a rough estimate for the lowest pH for water, we can start with water as 55.5 moles per liter. We would say that if we had a liter flask containing 100% hydronium, replaced all water molecules H2O with hydronium ions, H3O plus ions, and calculate the pH, we would find that the pH of negative log 10 55.5 equals negative 1.75. So we might say that the lowest pH is near negative 1.75. Of course, we neglected the possibility that a substance made of pure hydronium might have a different density than neutral water. Some acidic solutions are more dense than pure water because the added substances have a greater density to begin with. There are strong acids that can achieve acidity levels less than -1, notably some sulfuric acids. A very strong base might have a pH greater than 12. We must remember that pH is a log 10 scale, so a solution with a pH of 6 is 10 times more acidic than a pH of 7. A solution with a pH of 1 is 10 to the 6th or 1,000,000 times more acidic than neutral water with a pH of 7. Conversely, a solution with a pH of 8 is 10 times more basic than neutral water with a pH of 7. A solution with a pH of 13 is 10 to the 6th or 1,000,000 times more basic than neutral water with a pH of 7. Substances that cause water to become more acidic include hydrochloric acid, HCl, nitric acid, HNO3, and sulfuric acid, H2SO4. Hydrochloric acid, HCl, is stomach acid. Nitric acid, HNO3, is used to make nitroglycerin and fertilizer. Sulfuric acid, H2SO4, is the battery acid found in lead-acid car batteries. All of these acids are strong acids because each molecule completely dissociates from its hydrogen atoms when placed in water. And because of the complete dissociation, the reaction is a one-way reaction represented by a one-way arrow. And so we know the dissociation is complete. These strong acids have very large equilibrium constants, Ka. A strong acid is one with a Ka larger than 10 to the second power or a pKa smaller than -2. I show some reactions of acids with water. Hydrochloric acid has a Ka of 1.3 times 10 to the sixth or pKa of -6. Nitric acid has a Ka of 2.5 times 10 to the first or pKa of -1.4. Sulfuric acid has a two-stage dissociation with different Ka values for each hydrogen atom. For its first dissociation, sulfuric acid has a Ka of 6.5 times 10 to the 2 or a pKa of -2.8. For its second dissociation, sulfuric acid has a Ka of 10 to the -2 or a pKa of just 2. Mild acids all have Ka values smaller than 10 to the -2 or pKa's greater than 2. Some common mild acids include citric acid, acetic acid, and ascorbic acid. Citric acid is found in orange juice, acetic acid is found in vinegar, and ascorbic acid is vitamin C. I list the Ka values and pKa values for these mild acids here. Of importance to biology and biochemistry are the amino acids, that are the building blocks of proteins, and the nucleic acids that are found in RNA and DNA of cells. Both amino acids and nucleic acids are acids in the sense that they are both H+ donors. They are very mild acids. They serve very different roles in the body. DNA and amino acids are only related in that DNA code tells the amino acids how to link up to form useful proteins. I shall go deeper into nucleic acids and amino acids in a video on biology. On the base side, there are strong bases and mild bases. A strong base would be a base with a Kb of greater than 1 or a pKb of less than 0. The strong bases would include hydroxides of alkaline metals such as lithium hydroxide, sodium hydroxide, and potassium hydroxide. All these strong bases cause the hydroxide ion count to increase when they dissociate in water. Lithium hydroxide, LiOH, is a basis for the cathode material of lithium-ion batteries. Sodium hydroxide, NaOH, is a precursor chemical in the clothes bleach and many soaps. NaOH is also known as lye drain cleaner. Sodium hydroxide mixed into chlorinated water will yield sodium hypochlorite, a bleach. Solid KOH, also known as potash, is used for making soap. On the slide, I give the chemical reactions, the Kbs, and the pKbs for many of these strong bases. The reaction to make sodium hypochlorite bleach from sodium hydroxide and chlorine gas is as follows. Take a solution of 2 moles of NaOH and add 1 mole of chlorine gas. The product will be NaClO plus NaCl plus H2O. The aqueous AQ notation allows the reader to know that the reactants and products have dissolved into liquid water. There are many chemicals that act to remove a proton from H2O and increase the OH negative ion count in water solutions. Ammonia, NH3, causes an increase in hydroxide ions OH negative when dissolved in water. The ammonia reaction has a Kb of 1.8 times 10 to the -5 or a pKb of 4.75. The chemicals pyridine and methylamine also increase the OH negative count in water solutions. Pyridine has a Kb of 1.7 times 10 to the -9 or pKb of 8.77. Methylamine has a Kb of 4.6 times 10 to the -4 or a pKb of 3.33. Pyridine is a liquid at 25 degrees Celsius. Methylamine is a gas at 25 degrees Celsius. Both are foul, fishy-smelling chemicals. Pyridine is found in foul-smelling bodily secretion and is a byproduct of some cooking processes. Pyridine is used in processing herbicides and insecticides. Methylamine is found in rotting flesh. Methylamine is used in creating medicines as well as processing herbicides and insecticides. Viewers of the show Breaking Bad will recognize methylamine as the chemical that Walter White used to create his crystal meth drugs. Interesting things happen when acids are added to bases. Never mix acids and bases outside of a laboratory with good safety equipment. Some acid-base reactions result in violent explosions or the release of heat and poisonous gases or flammable gases. Most acid-base reactions result in the production of a salt and steam. The mix of hydrochloric acid, HCl, with the strong base, sodium hydroxide, NaOH, results in the formation of table salt, NaCl, with water, steam, and a great deal of heat release per mole of HCl. I show that reaction on the slide with 55.7 kilojoules per mole of energy released. The original reactants are already ionized in aqueous solution when mixed. There are lots of H+, Cl-, Na+, and OH ions in the separate solutions. As the solutions are mixed together, the amount of liquid water present will dictate how much the temperature will rise from the heat energy. The amount of liquid water present will dictate how much, if any, solid NaCl will precipitate out of the solution and fall to the bottom of the mixing beaker. Also, the amount of liquid water present will dictate how much water vapor will bubble to the surface or condense back into the solution as liquid water. The mix of sulfuric acid, H2SO4, with the strong base, sodium hydroxide, NaOH, results in the formation of sodium sulfate, Na2SO4. During the reaction, steam is created and a great deal of heat released per mole of H2SO4. In the reaction equation, I show that 1 mole of H2SO4 is mixed with 2 moles of NaOH. The products of the reaction are the sodium sulfate, the steam, and 112.5 kilojoules per mole of energy released. Again, the original reactants would have already been ionized in the aqueous solution before they are mixed. H+, SO4 - 2, Na+, and OH ions exist in separate solutions. As the solutions are mixed, the amount of liquid water present will dictate how much the temperature will rise from the heat energy. The liquid water present will dictate whether any solid sodium sulfate will participate out of the solution and fall to the bottom of the mixing beaker, and also how much water vapor will bubble to the surface or condense back into the solution as liquid water. Sodium sulfate is a salt, although not one meant for human consumption. Sodium sulfate's most common uses are to process paper and glass. All these acid-base reactions have equilibrium constants to tell us how far the reaction goes in either direction at any given temperature. These equilibrium constants might be guessed at by the electronegativities of the components. But there's no way to accurately calculate or predict what the equilibrium constants might be. Chemistry is just too complex to achieve the kind of accuracy we might expect from physics. Even for the simplest reactions of acids and bases, the equilibrium constants must be measured through experiment. These equilibrium constants are tabulated for many acid-base reactions. If the products of a reaction are known, the enthalpy difference or heat release during the reactions can be calculated from the tabulated values. Again, the enthalpy tables for the simplest chemical bonds must be measured experimentally. The bond enthalpies could be guessed at from the knowledge of bond energies of similar bonds. But all in all, chemistry is too complex for accurate predictions, and this is a limitation of the human understanding of nature. And that concludes my discussion of acids and bases. In my next video, I will focus on the chemistry of batteries and fuel cells. Thank you for watching. If you enjoyed this video and want to help me make similar content, please like and subscribe.
In the reaction of sodium hydrogen carbonate with hydrochloric acid, you will mass a 100 milliliter beaker. You will then add about 2 grams of sodium hydrogen carbonate to the beaker. You will remass the beaker and the sodium hydrogen carbonate to give you the mass of the sodium hydrogen carbonate. Add about 5 milliliters of water to the beaker. This will help to dissolve the sodium hydrogen carbonate. Gently swirl the beaker to get some or all of the sodium hydrogen carbonate in solution. We'll add a couple of drops of bromethymol blue indicator to the solution. Bromethymol blue is an acid-base indicator, is blue in basic solution and yellow in acidic solution. We will cover the beaker with a watch glass to minimize loss of compound due to splattering. We will slowly add 3 molar hydrochloric acid to the sodium hydrogen carbonate. The sodium hydrogen carbonate and the hydrochloric acid react to produce sodium chloride, carbon dioxide gas, and water. The carbon dioxide is released from the solution, which is the fizzing that we see. The water joins the water that's already in the solution, and the sodium chloride that's produced dissolves in the water. We can tell when we've added an excess of hydrochloric acid. When the solution turns yellow, all the sodium hydrogen carbonate dissolves and no more carbon dioxide gas is emitted. We take a little water and rinse off the bottom of the watch glass, and we rinse down the sides of the beaker to make sure that all the sodium hydrogen carbonate has had a chance to react. You will evaporate the water to leave the sodium chloride. You will mass the beaker and the sodium chloride to determine the mass of the sodium chloride.